Assalamualaikum and good morning. Today we continue non-reactive process energy balance. Changes in temperature in heat capacity is on both elementary chemical processes. So the term sensible heat signify that the heat must be transferred to raise or lower the temperature of a substance or mixture of substances. The quantity of heat required to produce a temperature change in the system can be determined from the appropriate form of the first law of thermodynamics. So we have Q equal to delta U. Delta U refers to internal energy. Delta H is the enthalpy. So the specific internal energy of a substance depends strongly on temperature. If the temperature is raised or lowered in such a way that the system volume remain constant, the specific internal energy might vary as shown in the following plot. So the temperature change delta T from T1 to T delta T so this is what we call a CV, or heat capacity of a constant volume. Since the plot of U versus T is not only a straight line, hyperbolic, CV, the slope of the curve, is a function of temperature. The change in U, temperature rise from T to T plus delta T or T plus dt at constant volume is from equation 8.3-3. And the change delta U associated with a temperature change from T1 to T2. So we have delta U, this is a specific internal energy equal to T1 to T2 CV delta T. Now suppose both temperature and volume of a substance change. To calculate delta U, you may break the process into two steps: a change in V at constant T followed by a change in V at constant V. So we have 2 delta U. So since U is the state property, so delta U equal to delta U1 plus delta U2. For ideal case, liquid and solid, U depend only on T. So since T is constant in step 1, delta U is approximately 0. So for any substance that a non-ideal case. Well, since the second step is a change in temperature at constant volume, this is referred to this one. given in 8.3-5. In summary, then, for a temperature change from T1 to T2, so we have ideal gas is exact delta U equal to ideal gas, or solid or liquid is good approximation. The value of the delta U, the non-ideal gas valid only if V is constant. Example. So calculate the heat required to raise 200 kg of nitrous oxide. This is a closed system. How do you know it's a delta U or internal energy? From 20 to 150 in dc in a constant volume vessel, the constant volume heat capacity of nitrous oxide in this temperature range is provided by the equation CV equal to 0.855 plus 9.42 times 10 to the power of negative 4 T. The textbook referred to page 413. With T is in degree C. From equation 8.3-6, this equation, this is a case. So delta U is expression from 20 to 150. Do the integration. Then you get delta U equal to 121 kilojoule per kg. The energy balance for this closed system, neglecting EK or kinetic energy, potential energy, and work, is Q equal to delta U equal to N kg multiplied with specific internal energy. Given in the question 200 kg multiplied, we get Q equal to 24200 kilojoule. Try this exercise. Heat capacity at constant pressure. Next. Previously, you learned about CV, or heat capacity at constant volume. Now it's a CP, heat capacity at constant pressure. Next, let's suppose that we heat a substance at constant pressure and consider the resulting change in enthalpy, like internal energy. Enthalpy depends strongly on temperature. If delta H is the change in specific enthalpy resulting from a temperature increase at constant pressure from T to T plus delta T, then as delta T approach to 0, the ratio delta H over delta T approaches a limiting value defined as the heat capacity at constant pressure, or equation 8.3-7. Similar method, constant pressure, constant temperature, this is constant pressure. The first step is a change in pressure at constant temperature. The type of process described in section 8.2, we saw in that section that delta H1 equal to 0, ideal case. For solid or liquid, it's a delta H1 equal to V delta P. So delta H1 is referred to here. Changes in temperature, changes in pressure, constant in temperature. Next is the second step here, delta H2. Changes in temperature, constant pressure. So that delta H2 is given equation 8.3-8. Finally, delta H is equal to delta H1 plus delta H2. So for ideal gas, nearly ideal gas or non-ideal gas, exactly only if this is the condition. So any type of gas, assuming it's fulfilling the condition, you can use 8.3-10A. Then for solid or liquid, you have the first expression with this delta H1. You see delta H1 for ideal gas is 0, but for the solid or liquid is a specific volume V multiply with delta P plus this expression. For all but large pressure changes and small temperature changes, the first term of equation 8.3-10b is usually negligible relative to the second term. So for large pressure changes, we can actually assume the first expression is negligible. Exercise. So if Cp for an ideal case, okay, is that value, what is the enthalpy change in calories responding to a change from 10 degrees C to 30 degrees C undergone by 5 gram of the gas? So this is referred to the first expression, this expression, because it's an ideal gas. So changes need to integrate 0.5 from 10 to 30. As you get the Cp, multiply with the gram. Yeah. Then you get the enthalpy change. Another exercise. Heat capacity formula. The heat capacity Cv and Cp are physical properties of material tabulated in reference such as Perry Chemical Engineer Handbook. They may be expressed in any unit of energy per unit species, amount, mass, or mole per unit temperature interval. For example, joule per mole Kelvin or BTU per pound mass Fahrenheit. The term specific heat is also used for this physical property. So when reading question of heat capacity formula from table B2, so table B2 is at the back of buku elementary chemical processes, page 635. So to read this table, do not mistake the orders of magnitude. If a value 72.4 is read from the column label B10 to the power 5, then the value of V must be 5 order magnitude less than the 72.4. So B is equal to 72 times 10 to the power of negative 5. If you refer to table B2, acetone there, A is equal to, sorry, you refer to column A times 10 to the power of 3. So the actual value for A is A equal to 123 times 10 to the power of negative 3. So you bring that 10 to the power of 3 to the left hand side. Then you get this 10 to the power of negative 3. Sebab dia bawa tepi jadi bahagi. Dan bahagi is actually negative 3. Yeah. The heat capacity function of temperature are frequently expressed in polynomial form. Cp equal to A plus BT plus CT square plus DT cube. That one referred to from in table B2 on the top. There are two forms. So form number 1 is Cp and with expression until dt cube. For form 2, it's until t to the power of negative 2. So how do you know which form should you use? You refer to the table. Refer to column number 5 then, form. Let's say calcium carbide here. Using the second form. So for the second form, you need to use the second equation. Value of the coefficient A, B, C, and D are given in table B2. That one is referred to column 1, 2, 3, 4, 5, 6. Column 7 until 10. Column 7 until 10 will give you the value of A, B, C, D. So for liquid and solid, Cp is equal to Cv. For ideal gas, Cp is equal to Cv plus R. That one is important. You can also estimate delta H or delta U using equation 8.2-2, 8.3-10, and 8.3-11. For the heating of cooling or cooling of any solid, liquid, or gas, whether or not the pressure change heat capacity formula given in table B2 may be integrated in this equation. So we have delta H U1 to T2. This is already given. This is similar. This is for the enthalpy. This is for the ideal gas. So for ideal gas, this is for internal energy, delta U. Ideal gas or gases close to ideal solid and liquid. So this one is delta U equal to 0. For delta H, ideal gas and gas close to ideal, delta H also 0. But for solid and liquid, it's delta H equal to V delta P. This is for gases. Difference between enthalpy and specific internal energy. You see there, the Cp is for delta H enthalpy. Cv for internal energy. So the equation here it's Cv. If the question only give you Cp, and since Cp is available in table B2, Cv is not. So you can use approximation here. Cp Tt minus R T2 minus T1. R is the gas constant. Now liquid and solid. This is for liquid and solid, delta H and delta U. So for delta H, it's two expression. For delta U, it's example, assuming ideal gas behavior. So it's a gas bomb. Calculate the heat that must be transferred in each of the following cases. A stream of nitrogen flowing at a rate of 100 mol per minute is heated from 20 to 100 degrees C. Nitrogen contained in a 5-liter flask at an initial pressure of 3 bar is cooled from 90 to 30 degrees C. Neglecting kinetic energy changes, the energy balance for the open system of part 1 is Q equal to delta H. And that for the closed system, the second part is the equation number 2, Q equal to delta U. Because this is nitrogen contained in a 5-liter flask, which is enclosed system. The problem is therefore to evaluate delta H and delta U for the two specified processes. From table B2, appendix B, the heat capacity of nitrogen at constant pressure of 1 atm is, okay, this is referred to table B2 for CP. Muka surat nitrogen 637, the first row. Pas sekali. So this is using form 1, this is for gas. So we have A, B, C, D. You see the value here? It's negative, 0.2199. 10 to the power of negative 5. Negative is important here. It's not positive. Alright. Since we are assuming ideal gas behavior, so delta H is equal to this expression. So delta H, substitute the value of Cp into the equation, do the integration, limit from 20 to 100, then we have delta H equal to 2.332 kilojoule per mole for the delta H. Okay, delta H. Next is delta U. The second question, nitrogen. To evaluate delta U, we need the number of mole n, which may be calculated using the ideal gas equation of state, and delta U, which we calculate from equation 8.3-B. Since there are no CV given, so we need to approximate using CP. If you use CP, then you need to include the ideal gas constant, or the gas constant, R. Yeah. So the expression here, the first one, CP is the same. This expression is the same, but the temperature is not 90 to 30. It's cool from 90 to 30. Okay. So delta U equal to negative 1.25 kilojoule per mole multiply with N. So N here we use PV equal to nRT, which is the gas equation of state, Q equal to negative 0.621 kilojoule. Question 2. The case constant R is equal to 2 calorie per mole Kelvin if Cp for vapor is 7 calorie mole degree C. Estimate Cv for the vapor if Cp for liquid is 7. Okay, dah nak. Estimate Cv for the liquid. Oh, liquid. If Cp for liquid is 7 mole, okay, estimate Cv for the liquid. So for the liquid is easy because for liquid Cp is equal to Cv. So 7 calorie per mole degree C for Cp liquid is equal to Cv for the liquid, but for the ideal case, you need to use equation 8.3-11b Cp equal to Cv plus R. So Cv for vapor is 7 minus 2, 5. Alright. So when enthalpy must be calculated frequently for a physics, it is convenient to prepare a table of delta HT for the species as was done for water in the steam tables to avoid having to integrate the formula for CPT again and again. Table B8 and B9 in appendix B list specific enthalpy of uh, uh, the value on this table are generated by integrating CPT from specified reference state. But oh, table B8 and B9. Okay. Table B8 and B9. Oh, okay. So this is CP, specific enthalpy, delta H. Mm, So to get this value in table B8, B9, we by getting CPT from specified reference state 25 degree C. This is based on this table or 77 degree Fahrenheit for US unit to the listed temperature. Okay. Example 15 kilomole per minute of air is cooled from 430 degrees C to 100 degrees C. Calculate the required heat removal rate. Using heat capacity from table B2 or table B8 or the apex function. That one is for the software. The hardware, they say, which is from table B2. So this is air. So air saya atas sekali itu. Acetone. Yeah. Air is row number 3 deh. page 635, table B2. So this is air in degree C, okay. Then you use the first the degree C row. You calculate CP like this. Extract the A, B, C, D. Don't forget it's negative. 10 to the power of negative something. Integration limit from 430 to 100. Do the integration. Substitute this value. Then you get negative 9.98 kilojoule per mole. The easy way is table B8. So table B8, page 652. This is based on SI unit. So find A. A is the second column. Temperature is 100 first, 2.19. Then another temperature is 430. Yeah? So enthalpy for A at 100 degrees C can be directly read from table B9, and enthalpy at 430 can be estimated by linear interpolation from the value 400 and 500. This is the interpolation. So H 430 degrees C equal to 12.17 kilojoule per mole. Then just add. So 2.19 plus, minus, because it's a delta H. Okay. You get negative 9.98 kilojoule per mole. Estimate the specific enthalpy of steam at 100 degrees C and 1 atm relative to steam at 350 degrees C and 100 bar using the steam table. Next is using the table B2. So for steam table, the table start with table B3, so B5 lah. B5. So since this is based on 100 degrees C, use the table B5. Easy. Table B5 100. Apa ya? Specific enthalpy ya. 1, 2, 3, 4. Oh, the last column. Yeah. It's first enthalpy at 100 degrees C is 2676. Then it says here relative to steam. So steam at 350 degrees C. So you need to find 300 degrees C. Since table B5 is until 102 degrees C, you need to refer to table B6. Table B6 depend based on pressure table. But you can look at the second column. It's in temperature. Cepat cukup ke situ? 350. Masih dapat jawab. Yes, ada. So there are no temperature steam at 350. So you need to do interpolation between 349 and 352. But the value is between 2551 to 568. Let's say it's 2560. So 2560 minus 2676. Yeah. So that is the method using Steam table. Next is 100 bar. Oh, it's easier using table B7. Yeah. For the question A there, 100 bar using table B7, page 150. 100 bar, the first column. So in the first row, you search for 350 degree C. So value of H is 2926. So 2926 minus 2676. Next method is using prior. Table B2, steam. Steam. Okay. So steam is water. Water in gas form. So you use the last row. The last table for table B2 is page 337. The last row. So this value transfer it to form number one. Equation in the first form. Don't forget it's negative. 10 to the power of negative something. Then do the uh, integration from 100 to 350. Just that in table B2. Okay, this is just uh, substitute value. Refer to table B2. The enthalpy listed in table B8 and table B9. For that matter, the heat capacity formula of table B2 and enthalpy function of apex applies strictly to heating and cooling at constant pressure of 1 atm. The tabulated enthalpy and heat capacity may also be used for non-isobaric heating and cooling of ideal or nearly ideal case. However, at high pressure enough or low or temperature low enough for the gas to be far from ideal table, enthalpy table or more accurate estimation should be used. Okay. This is for table B8 and B9. What is for? To calculate certain species of enthalpy. Estimation of heat capacity. The polynomial expression Cp in table B2 is based on experimental data for the listed compound and provide a basis for reasonably accurate estimation of enthalpy changes. Several rougher approximate methods follow for estimating heat capacity in the absence of tabulated formula. So in the absence of tabulated formula, like the one that you saw in table B2, so you can do the estimation of heat capacity, Cp. The first method is a Kopp's rule. Kopp's rule is a simple empirical method for estimating the heat capacity of a solid or liquid at or near 20 degrees C. According to this rule, Cp for a molecular compound is the sum of contribution for each element in the compound. For example, the heat capacity of solid calcium hydroxide CaOH2 would be estimated from Kopp rule as something like this. So to get the CPCA, that one you need to refer to table B10. Let's see. Table B10. Appendix B, last kali. The last table. Okay, so table B10, we have not all element CHB, SiO, FPS. This carbon, hydrogen, boron, silicon, oxygen, yeah, P phosphate, sulfur, fluorine. Beside this element, there are another general element is under all others. So for CPA of Ca, it's what is it? Is it solid? Okay, solid. Solid calcium hydroxide. So solid is 26 plus 2 CP. Oxygen is available. So 2 times 17 plus CP for hydrogen is 9.6. Confirm in table B10. Yeah. So 2 here refer to this yeah, chemical chemical expression. So CP for solid calcium hydroxide approximately equal to 79 joule per mole degree C. The true value is 89.5 joule per mole degree C. Not sure where to get this value, but normally it's available in Perry Chemical Engineering Handbook, Volume 2. So enthalpy change approximation. Suppose you wish to calculate the enthalpy change associated with a change in temperature undergone by a mixture of substances. Enthalpy and heat capacity of certain mixture are tabulated in standard references. This is based on Perry Chemical Engineering Handbook, the second volume. Like in such data, you may use the following approximation. Rule number 1. Previously, you learned Cobb's rule. This is another method. Rule number 1, for a mixture of gases or liquids, calculate the total enthalpy change as the sum of the enthalpy change for the pure mixture components. You are in effect neglecting enthalpy changes associated with the mixing of the component, which is an excellent approximation for mixture of gases and for mixture of similar liquids such as pentane and hexane, but a pure one for dissimilar liquids such as nitric acid and water. Rule number 2, for highly dilute solution of solid or gas in liquid, neglect the enthalpy change of the solute. So here solute refer to solid or gas. The more dilute the solution, the better this approximation. Okay. The example. Calculation heat capacity of a mixture. The calculation of enthalpy changes for the heating or cooling of a mixture of known composition may often be simplified by calculating a capacity for the mixture in the following manner. So at point 3-13, so Cp mix equal to summation of YICPIT. So Cp mix equal to capacity of the mixtures. Yi is the mass, a mole fraction of the component. So of the mixture, each mixture, sorry, each component or element have their own mole fraction or mass fraction. Cpi is the heat capacity of that specific component. So if Cpi and Cp mix are expressed in molar unit, then Yi must be a mole fraction of the I component. So it's vice versa. If it's in mass unit, then mass fraction. Once Cp mix is known, delta H for a change in temperature from T1 be calculated as this equation 8.3-14. Equation 8.3-14 is valid to the extent the enthalpy of mixing may be neglected. Example, calculate the heat required to bring 150 mole per hour of a stream containing 60% C2H6 ethane. Then we have 40% C3H8 or propane by volume from 0 degrees C to 400 degrees C. Determine a heat capacity for the mixture as part of the problem solution. Neglecting changes in potential and kinetic energy and recognizing that there is no shaft work involved in the process, the energy balance become Q equal to delta H equal to N multiply delta H. So this is the delta H for red. This is for the specific enthalpy where delta H equal to 0 to 400 degrees C. Cp mix dt, the polynomial expression for the heat capacity of ethane propane given in table B2 are given equation 8.3-13. Okay, this expression. So simplify the equation because it's a Cp mix. Yeah, meaning expression Cp for ethane plus expression Cp for propane, then you simplify, meaning solve it in T, then put it in equation, do the integration from 0 to 400, we get 34.89 kilojoule per mole. If there is no potential and kinetic energy and shaft work, so we can say Q equal to N delta H. So Q equal to 5230 kilojoule per hour. Exercise. Okay, number two. 2 kilogram of liquid nhexane CP and 1 kg of liquid cyclohexane are mixed heated 120 to 30 degrees C. Use the rule for liquid mixture rule 1. Given in this section to show that delta H equal to 68 kilojoule per kilojoule for this process. What is delta H? Kilojoule per kg. So rule 1 says that for a mixture of gas or liquid, calculate the total enthalpy changes as the sum of the enthalpy changes for the pure mixture. So the sum mean you need to add up 2.5 plus 1.8. So since this is CP, so you need to do some integration from 20 to 30 of for the summation of 2.5 and 1.8. Berapa? Ada. So you don't sum it. It's you need to do it individually, but at the end sum the value. So for example, CP here is from 20 to 30. There's a 2 kilogram. So you get 2.5 multiply with 10 multiply with 2 gram. Another one is 1.8 multiply with 10. Then you add these two, you get 68 kilojoule. So what is the delta H per kg mixture? So divide by 3. Yeah. 68 divided by 3. So that is the specific enthalpy. Energy balance on single phase system. Okay. We are now in position to perform energy balance on any processes that do not involve phase changes. Mixing step for which enthalpy changes cannot be neglected or chemical reaction. If a process only involves heating or cooling single species from T1 to T2, the procedure is straightforward. So evaluate delta U or delta H. So for the closed system, delta U equal to N delta U refer to specific internal energy. Okay. Number 3, substitute delta U, delta H, and delta H. If more than one species is involved. Oh, wait. Okay. If more than one species involved, or if there are several input or output stream instead of just one of each, the procedure is given in section 8.1 should be followed. Choose reference state, in table. One is already here. The example is the procedure for a continuous heating process. A stream containing 10% methane and 90% air by volume is to be heated from 20 to 300 degrees C. Calculate the required rate of heat input in. If the flow rate of the gas is 2 times 10 to the power negative 3 liter STP per minute. So solution assume ideal gas behavior. So 2000 liter STP per minute. Enter the heater. We only know the fraction. Not sure what the model. Okay. Don't know N. Okay. Then after heating, temperature to rise to 300 degrees C. The fraction between methane and A is the same. To determine the N, since this is 2000 liter STP, standard temperature pressure, so we can relate it to 22.4 STP. Then we get the N or mole flow rate equal to 89.3 mole per minute. From here, to create the table, choose the reference. In this case, the reference is inlet. Inlet for methane, 25 degrees C for air. Memilih 25 degrees C. Mau sebab kah? Oh. So this question choose specific reference temperature of 25 degrees C for A because of table B8. Yeah. So the reference condition for methane oxygen so that delta H in could be set to equal to 0, which is yes. Since temperature is the same. So delta T is 0. And that for A was chosen so that delta, so H in and H out could be determined directly from the table B8 is easier. The next step, if you use table B2 is can as well, no problem. But you need to do the integration. The next step is to evaluate all of the unknown specific enthalpy in the table. H1, for example, is the specific enthalpy of methane. H1T. Okay, H1 is methane out. The air is H2 and H3. Yeah? Oh. So CH4 methane gas from 20 degrees C 1 atm to gas from 300 degrees C. P in outlet mixture. Okay. So for the methane, so the CP is from table B2. Always remember 10 to the power of negative. Then get 12.07 kilojoule per mole. This is H1, enthalpy 1. Right? Next is enthalpy 2, enthalpy 3. That one refer to table B8, page 652. So H2 equal to negative 0.15 kilojoule per mole. H3 is 8.17 kilojoule per mole. The energy balance now yield Q equal to delta H. So N out, H out minus H in. So this value is from the table that you have calculated. So this is for the H out. In this case, H out sikit. H out ada dua. H in sikit. Okay. Yes. Ada. So Q equal to 12.9 kilowatt. In the last example, the temperature of all input and output stream was specified, and the only unknown in the energy balance equation was the heat transfer rate required to achieve the specified condition. You will also encounter problem in which the heat input is known but the temperature of an output stream is not. For this problem, you must evaluate the outlet stream component enthalpy in terms of the unknown T. So this is quite panjang. Yeah, because we find the T inside the CP. Nah, tak nak situ. Let's start. No ignition dia. Oh, okay. Exercise, huh? Exercise. Should dia ajak HA. Reference dah bagi. Follow dia. So this reference H2O is based on the triple phase point. Triple point in the phase diagram or water phase. For the propane is 40 degrees C, which is the inlet. 40 degrees C. Okay. Example 5. Panjang. Panjang cerita. What does it want? Calculate the temperature of gas leaving the exchanger using data from table B1 and B2 but not using apex. Temperature leaving the heat exchanger. Okay, here. Oh, here. See, sorry. Inlet is 500 degrees C. Outlet is T. The same thing. Do the material balance, if any, since it's not required in this question. So no need. Okay, so reference is CO is 500 degrees C. This is the inlet for CO. For carbon dioxide is 500 degrees C. Same, this is inlet. H2O is at triple point. All right. So how many H? 4 H. Sorry, 4 enthalpy need to calculate. So the solution strategy will be calculated H1 and H2 by integrating the heat capacity formula of table B2. Since we don't know temperature outlet now, so this yeah. So the expression is in T, like this. It's in T, H1 and H2. Because you cannot solve. You see, 500 to T, 500 to T. The H3 and H4 is water. One is can refer to a steam table. So in order to use steam table, the reference condition must be at triple point. Okay. Pagi. So we cannot leave it in this expression. So you need to do the integration. So once you do the integration, substitute this value 500 to T. So meaning T minus 500 lah. It's very what tedious. Integrate, substitute value. So leave the value in T, then you add up everything. H1 plus H2 plus H3 and H4. Yes. Q is berapa bagi Q kah? Or since this his exchanger is operate adiabatically, so Q equal to 0. No, that's two. This one. Operate adiabatically. So Q equal to 0. So Q equal to delta H equal to 0. So this is the final expression after you put H1, sorry, after you sum H1, H2, H3, H4. So you get this expression. The expression you need to solve it. You get either using the Excel or the latest calculator, scientific calculator you can calculate that. Yeah. So T here is 299 degrees C. So meaning the temperature from 500 to 299. All right. Okay. So this exercise, yeah, using the same method. You see, temperature. Uh, but in this case, the Q is given. Heat is lost from mixture to something. equal to 7 kilowatts, so negative 7 kilowatt. So negative 7 equal to the expression in T. Then you need to solve that one. Wait. Now it's a phase change operation. It has a turn. Any question you can ask. Yeah, no need to wait to finish. Open my laptop there. Close window. Okay. So continue phase change operation. This is page 424. So consider liquid water, water vapor each at 100 degrees C and 180 atm. Which would you expect to be greater, U liquid or U vapor? We call it U internal energy is related among other things to the energy of motion of the individual molecule at the specified condition. If you said U vapor, you would be correct. One way to think of it is that one way to think of it is that the molecule of vapor, which can move around relatively freely, much more energetic than the densely packed molecule of a liquid at the same temperature and pressure. Also think about the fact that liquid molecules are held in close proximity to each other by attracting force between the molecule. The energy required to overcome this force when the liquid is vaporized is reflected in the higher internal energy of the vapor molecule. Inspection of table B5. Table B5 is a steam table. Reveal how dramatic the difference between new liquid, internal energy of liquid, internal energy of vapor. Water at 100 degrees C and 1 atm U liquid is 419. U vapor is 2507 kilojoule per kilogram. The difference in specific enthalpy, to U plus PV is even greater. So this is H equal to U plus PV. It's even greater owing to the much greater specific volume of the vapor at the same temperature and pressure. Ya, value lebih kurang juga. But HB is higher. The phase change such as melting and evaporation are usually accompanied by large changes in internal energy and enthalpy. As in the example just given, heat transfer requirement and phase change operation consequently tend to be substantial since Q is equal to delta U. So closed constant volume system or Q equal or approximately delta H for open system. The paragraph that follow outline procedure for setting up and solving energy balance on such operation. The discussion will be limited to phase change between liquid and vapor, evaporation, condensation, liquid, solid and liquid, melting, freezing. However, the method may be extended directly to other phase changes such as sublimation and conversion from solid phase to another, from amorphous to the crystalline. So we have latent heat. The specific enthalpy change associated with the transition of substance from one phase to another at constant temperature and pressure is known as latent heat of the phase change, as distinguished from sensible heat, which is associated with temperature changes for a single phase system. For example, the enthalpy change delta H for the transition of liquid water to steam at 100 degrees C and 1 atm, which equal 40.6 kilojoule per mole, is by definition the latent heat of vaporization. Okay, or simply the heat of vaporization. So this heat of vaporization, it is available in table B1 actually. It's delta cik gila tu. Delta HV. Delta HV. Cik delta HV atas. Refer table B1. Since condensation is the reverse of vaporization, and enthalpy is a state property, the heat of condensation must be negative to the heat of vaporization. So, although in table B1 is you can only see delta HP or heat of vaporization, but heat of condensation is the same value but with negative negative value. Yeah. So in this case, heat of condensation of water at 100 degrees C 1 atm is equal to negative 40.6 kilojoule per mole. Similarly, the heat of solidification is the negative of the heat of fusion at the same temperature and pressure. Latent heat for the two most commonly encountered phase change are defined as follow. Heat of fusion or heat of melting, delta Hm, also available in table B1. Is the specific enthalpy difference between the solid and liquid form of a species at T and at temperature and pressure? So we have heat of vaporization, delta HVTP. Latent heat of a phase change may vary considerably with the temperature at which the change occurs, but hardly varies at all with the pressure. At the transition point, for example, the heat of vaporization of water at 5 degrees C is 2442.5 joule per gram. At pressure 23.78 millimeter mercury and 2442.3 joule per gram. That one is at atmospheric. So when using a tabulated latent heat, you must therefore be sure that the phase change in question takes place at the temperature for which the tabulated value is plotted, but you may ignore moderate variation in pressure. So for that specific value like delta HV, delta apa ya? Delta HM, delta HV is related to temperature of boiling or TB in table B1 for delta H HM, M refer to melting is melting temperature. Example 1, at what rate in kilowatt must heat be transferred to a liquid stream of methanol at its normal boiling point to generate 1500 gram per minute of saturated methanol vapor. So from table B1, delta HV is 35.3 kilojoule per mole at TB or boiling point 64.7 degrees C. You can refer to table B1 to check. The energy valence with potential kinetic energy changes neglected. So Q equal to delta H equal to N delta HV. So 1500 grams methanol per minute multiply with atau molecular weight, then 35 kilojoule per mole from the delta HV. This is unit conversion. Then we get Q equal to 27.6 kilowatt. Do the exercise. Sama. Calculate latent heat of phase change at any temperature. Okay. Phase changes often occurs at temperature other than the temperature for which the latent heat is tabulated. When faced with this situation, you must select a hypothetical process path that permits the available data to be used. Suppose, for example, that a substance is to be vaporized isothermally at 130 degrees C, but the only available value of the heat of vaporization is at 80 degrees C. A process path from the liquid at 100 degrees C to the vapor at the same temperature must then be chosen. That include an isothermal vaporization step at 80 degrees C. Specifically cool the liquid from 130 to 80. Vaporize liquid at 80. Heat the vapor back to 130. Summing the changes in enthalpy for each of these steps yield the change in enthalpy per given process. Okay. Later the example like this. So 100 gram mole per hour of liquid and hexane, 25 degrees C, 7 bar is vaporized. The word vaporize means to change the form from liquid to gas. and heated to 300 degrees C at constant pressure. So there are phase changes here. So energy balance Q equal to delta H. Other expression is 0. Okay. So this is the method lah. Yeah. So this is just ignore this one. No need to show. Yeah. Just follow the available data from table B1. Okay. State 1 is the initial state, liquid N-hexane or liquid hexane, 25 degrees C, 7 bar. So we cannot follow CF because the data is not available. So in this case, we need to raise the temperature of liquid from 25 to 16. We raise to 69 because hexane boil at 69 degrees C. Ni hexane kutip. Hexane is in table B1, page 631. Yeah, 68.74. So approximately 69 and hexane. So you heat it up until 69. At 69 degrees C, it's still liquid form. The question asking us to vaporize it, so to change it from liquid to vapor. So A here is using CP. So CP you get from table B2. You do the integration from 25 to 69. Oh, but phase change. So for phase change here is refer to the table B2 delta HV. So D here path D refer to delta HV. Next is now the phase is changed at state 5. Yeah. So the final temperature is 300 degrees C. So now it's 69 still, but the phase is in vapor form now. Need to increase the temperature to 300 degrees C. So here we use well, here we use table B2 CP to calculate puff G. So integration of the CP from table B2 from 69 to 300 degrees C. So explanationnya is the same thing. Okay. So this is the first path A. Oh, since this is a liquid, so I forgot about the expression V delta P. So from table B1, Hg, specific gravity for N-hexane is 0.659. So rho is 0.659 kg per liter. Then table V2 we determine the CP from 35 to 69. Hexane, hexane, hexane harus sikit value. Oh ya, one value aja. 0216.3 times 10 to the power of -3. That's fine. 0.2163. Yeah. Otherwise, it should be in T lah. Many A, B, C, D. Yeah. Okay, so HA 9.44 kilojoules per mole. Then you calculate for D. D is delta HV. Directly take it from table B1. Then the last path is G. 69 to 300 degrees C. Like this. Since this is in vapor form, so expression for vapor form normally it's longer, involving T to power T cube. So solve it. Hg equal to 47.1, then add it up, all of it, Q equal to 85.5 kilojoule per mole. So Q equal to 2.3 at kilowatt. So if a phase change takes place in a closed system, you must evaluate delta U equal to delta H minus delta PV for the phase change to substitute into the energy balance equation. For phase changes such as fusion, which involve only liquid and solid, changes in PV are generally negligible compared to changes in H, so that delta U M is equal to delta H M. The one is for melting M or fusion. For vaporization, PV for the vapor, which equal to RT if ideal case behavior may be assumed. Wait, so that delta PV equal to RT. So delta UV equal to delta HP minus RT. This is for the vaporization. Okay. Exercise. Oh, check table B1. Phase change in closed system. Okay. If a phase change takes place in a closed system, you must evaluate U equal to delta H minus delta PV for the phase change substituted into the energy balance equation. For phase changes such as fusion, which only involve liquid and solid, changes in PV are generally negligible compared to changes in H. So did delta, okay, itu kan dah ada kah? Oh, okay. If you are given value of heat evaporation at 100 degrees C at 1 atm, would you be confident about using it to estimate the enthalpy change for vaporization at 100 degrees C and 2 atm? What about 200 degrees C and 1 atm? For the first 100 degrees C to atm, yes, confident because changes in pressure normally negligible. For changes in temperature, not confident. Yes. Okay. Boleh buat ni. Estimating latent heat. Previously, you learned about how to estimate CP. Now it's to estimate the latent heat, or specifically delta HP and delta HM. So for simple formula for estimating a standard heat of vaporization, delta HP at the normal boiling point is through turn rule. Delta HV approximately 0.88 TB. TB refer to boiling point. So this is in Kelvin. That one is for the non-polar liquid. For water or low molecular weight alcohol, you use this approximation. Norton rule provide an estimate of delta HV accurate to within 30%. Another rule that provide roughly 2% accuracy is Chen equation. So for Chen equation, doesn't matter. It's either if it's non-polar or polar liquid or alcohol, you can just use this equation. So TB is the boiling point. TC is the critical temperature. So critical temperature is available in table B1. PC is the critical pressure. That's it. Pun ada juga. Table B1. PC. For a formula for approximating a standard heat of fusion or heat of melting, so refer to this condition. In many cases, the heat of vaporization varies considerably with temperature invalidating equation 8.4-6. It is necessary to use the Clapeyron equation, from which equation 8.4-6 was derived. For equation 6.1-2, so we get this equation. But to use this equation, you need to plot apa ya? Plot vapor pressure. This is silap table B4. Table B4. That. Yeah, yes. Table B4 using Antoine equation. Page, yeah, panjang lah. Page 640. A useful approximation for estimating delta HV at temperature 2 from a known value of T1 is Watson correlation. So Tc is the critical temperature. Example. Okay, Truton rule. A normal boiling point of methanol is 337.9 Kelvin and its critical temperature and pressure are 5.3.2 Kelvin and 78.5 atm. The heat of vaporization at the normal boiling point is 35.3 kilojoule per mole. Estimate the heat of vaporization at 337.9 Kelvin using Truton rule and chain equation and determine the percent error for each estimate. Next is using Watson correlation, estimate the value of heat of vaporization of methanol at 200 degrees C using the measured and estimate value of the at the normal boiling point. Determine the percent error for each estimate if the measured value is 19.8 kilojoule per mole. So for the Truton rule, this is part of methanol. So methanol is low molecular weight alcohol. So you use the second expression for the Truton rule 0.19 TB. For chain equation, that one is doesn't matter, just plug in the value. But TC, PC, you need to refer to table B1. Okay, same lah. How would you estimate delta HB for a pure hydrocarbon at its normal boiling point under each of the fluid? You only, or you know only the normal boiling point. Truton rule. Enabling process involving phase changes. So when writing, sama aja method tu. Ya, sama aja. Equimolar, liquid mixture of benzene. Okay, at 50 degrees C. This. So the upper outlet is this specifically for the vapor? No, di atas. This is for the liquid. Kalau if you fill up, then it's marks deduction. In case it's come out in test or assignment. So for the inlet is equimolar, meaning 50% benzene, 50% toluene. But for the liquid product here, it's 40% benzene, and for the vapor product di atas, on the top, it's 68.4 more percent benzene. So since there are NV and NL here, then you need to do the mass balance. So this is the mass balance to identify the NV and L. Why you need to identify NV and L? You need to calculate the mole for benzene, toluene in liquid and vapor form here. So previously or before you do the mass balance, you don't know the value of NV and NL. So from the value NV and NL that you calculate, you can determine the actual mole for each of the substance. Reference is 10 degree C, 10 degree C. Siapa tu? Oh, inlet. So both of this is inlets. That's why H in is equal to 0. You need to calculate H1 until H4. The table is important. Mm. So to calculate H1, you use changes in temperature. Use the table B2 CP. H2 also CP. That one is for the toluene. Table H3. Sorry, enthalpy 3 or H3. This is phase changes. Why phase changes? It started from liquid for the reference state at 10 degrees C, right? Then end up at 50 degrees C. Yeah. This is for benzene in vapor form. So you see, this is for the liquid using the CP. Then you do the phase changes. This is from table B1, delta HV. But the temperature here is 80.1. You need to reduce it to 50. This is the target temperature lah for the outlet of the benzene. Similar for the toluene. So yeah, so the engine valence is Q equal to 17.7 kilojoule. Liquid stream containing 50 more percent benzene. Oh, okay, this is the exercise. Hmm, 44 dah. Ini ada 4 dah. Sekolah tercatat dah. Hmm. 45. Betul. Hmm. Okay. So now it's mixing solution. Skip the psychometric chart. Mana you dan psychometric chart ni? Uh, Ni apa ya? Fit in mass transfer, focus, unit operation. Focus on the energy balance part. So mixing and solution. So may I have carried out an experiment in a chemistry laboratory in which you mix two liquids, such as concentrated sulfuric acid and water, or dissolve a solid in a liquid such as sodium hydroxide and water, and observe that the mixture of solution become quite hot. The question is why. Wait. Mm. Okay. So when two different liquid are mixed, or when a gas or the solid is dissolved in liquid, bonds are broken between neighboring molecule and possibly between atoms of the feed material, and new bonds are formed between neighboring molecule or ion in the product solution. If less energy is required to break the bond in the feed material, that then is released when the solution bond form a net release of energy result. Unless this energy is transferred from the solution to its surrounding as heat, it goes into raising the solution temperature, which is what happened in the experiment described in the first paragraph. Oh. So suppose you mix 1 mole of pure liquid sulfuric acid with water at a specified temperature and pressure, and then cool the mixture at constant pressure. To bring it back to the initial temperature, the energy valence for this constant pressure process is Q equal to delta H equal to H2SO4 equals minus enthalpy H2SO4 liquid plus enthalpy water, where the delta H, the difference enthalpy of the solution at the specified temperature and pressure, and the total enthalpy of the pure solute and solvent at the same temperature pressure is the heat of solution. At that temperature and pressure, for the sulfuric acid dilution, we know Q is less than 0. The container must be cool to keep the solution temperature from rising, so it follows that delta H, the heat of solution, is negative for this process. Dah masuk weird one. Then we have the ideal mixture. This one for which the heat of mixing solution is negligible, and so delta H mixture is equal to NiHi summation of NiHi. So I refer to the component. So this assumption work well for nearly all gas mixture and for liquid mixture of similar compound, such as paraffin or aromatic. Okay. Heat of solution and mixing. H444. So the heat of solution delta H is defined as the change in enthalpy for a process in which 1 mole of a solute gas or liquid is dissolved in R mole of a liquid solvent at a constant temperature T. As R become large, delta Hs approaches a limiting value known as the heat of solution at infinite dilution. The heat of mixing has the same meaning as the heat of solution when the process involves mixing two fluid rather than dissolving a gas or solid in a liquid. Okay. As an illustration of how to use this data, suppose you wish to calculate delta H for a process in which 2 mole of potassium cyanide, KCN, is dissolved in 400 mole of water at 18 degrees C. First, calculate the mole of solvent per mole of solute. So 400 divided by 2. So 200 mole H2O per mole of KCN. The value of delta H is, or heat of solution, 18 degrees C are equal to 200. Available in table B B apa tu? B11 table B11. So table B11 is the heat of solution and mixing at 25 degrees C. So 25 degrees C refer to the uh, yeah, reference temperature. Okay. Delta H is listed as negative 3 kCl. Value of the if delta H is 18 degrees C, 18 degrees C, at R equal to 200. 200. The total temperature is therefore 2 mole KCN multiplied with 3 KCl per mole KCN. Okay. Sini dapat beli. Table B11 is limited to HCl, sodium hydroxide, and NaOH, and sulfuric acid, H2SO4. Table B11 is value of heat is okay of mixing SO4 in water. An assertion such as those given in table may be used to determine directly the specific enthalpy of solution at 25 degrees C relative to the pure solute and solvent at this temperature. Okay, that's all for this week. Later, I need your help to create a group lah in WhatsApp so that we can discuss when to conduct the test one lah. We stop it. It's like 8. If possible, by next week, this one. Thank you.